Hey everyone, and welcome to This Explainer. Today, we're diving into what is honestly one of the most fascinating, high-stakes supply chains on the entire planet. I'm talking about the nitrogen cycle. We're going to unpack the invisible infrastructure that literally builds life itself. And trust me, there is an incredibly frustrating paradox at the heart of it all.
Now, to really grasp this paradox, we've got to start by just looking up. Go ahead and take a deep breath. Okay, so 78% of the air you just breathed in, that's nitrogen. Our entire atmosphere is literally an ocean of this element. It's everywhere.
So let's dive into this, because here is the central mystery of our story. If we are practically swimming in an atmosphere made of 78% nitrogen, why in the world is a lack of nitrogen the #1 reason plants starve? Like, why do farmers and gardeners have to constantly add it to the soil?
Well, to solve this biochemical mystery together, here's our roadmap. Number 1, the foundation of life, nitrogen. 2, famine in abundance. 3, the nitrogen-fixing heroes. 4, chemical transformation in soil. And finally, number 5, losses and natural balance. Let's get started.
Section 1, the foundation of life, nitrogen. Before we figure out why plants struggle to get it, we need to know why they're so absolutely desperate for it in the first place.
You see, nitrogen is the absolute building block of a plant's vitality. It's the core of their amino acids, nucleic acids, and carbohydrates. It is literally what lets plants form chlorophyll, which gives leaves that beautiful, rich, dark green color. If you're growing crops, nitrogen is the thing that plumps up those grains and boosts protein. Or think about vegetables like lettuce or radishes. Nitrogen is the secret ingredient that makes them delightfully crisp and juicy. In fact, a healthy crop plant actually holds up to 4% nitrogen right in its leaves.
But what happens when that balance is off? Well, the consequences are pretty stark. A plant starved of nitrogen gets pale and stunted. We're talking thin stems, low protein, and weirdly high sugar. But on the flip side, more nitrogen isn't always better. An excess of nitrogen triggers this rapid but super weak growth. It makes plants incredibly vulnerable to wind, rain, fungi, you name it. In veggies, too much nitrogen absolutely ruins the taste and smell. And even worse, it can cause toxic nitrates to build up in the leaves, which is dangerous for grazing animals and, well, us.
Now, if you're out looking at your own garden, you really want to watch out for something called chlorosis. Because nitrogen is a highly mobile nutrient inside the plant, a starving plant will literally cannibalize itself. It strips the nitrogen out of its older bottom leaves and ships it up to the new growing tissues. That's why the very first warning sign of a nitrogen crash is the yellowing or chlorosis of those older leaves before they just drop off entirely.
Moving on to Section 2, famine in abundance. We know plants desperately need this stuff, but to understand why they struggle to find it, we have to look at where Earth's nitrogen is actually hiding out. Check out the staggering reality of Earth's nitrogen distribution. 98% of all the nitrogen on Earth is completely, utterly inaccessible to living things. It's trapped deep underground inside volcanic rocks. It has absolutely zero interaction with the soil, plants, or water. So everything we consider part of the biological cycle, the entire biosphere, is just scraping by on that remaining 2%.
But wait, what about that 78% of the atmosphere we were just talking about? Well, atmospheric nitrogen exists as N2. That's 2 nitrogen atoms locked together by a triple chemical bond. And this bond is incredibly rigid. We're talking one of the strongest chemical bonds in all of nature. Plants just don't have the biological tools to break that shield apart. So they sit in this vast sea of nitrogen completely locked out of the abundance. Talk about frustrating. So plants are forced to look down into the soil. But here's the catch. Surface soil contains only a tiny fraction of nitrogen, roughly 0.02 to 0.5%. The vast majority of the nitrogen that's actually available in the soil ecosystem is locked inside organic matter, which sits at about 5% nitrogen. Up to 99% of soil nitrogen is tied up in organic compounds like proteins and amines. So it's protected, it's safe from washing away, but again, plants can't just eat it directly. It is held super tightly by the negative charges of clay and humus surfaces.
Which brings us to Section 3, the nitrogen-fixing heroes. This is where we get to introduce the microscopic alliances that finally bridge the gap between that untouchable atmospheric nitrogen and our starving plants.
To put this into perspective, 140 million tons. That is the colossal scale of this hidden ecosystem. Every single year, microbes pull 140 million tons of inorganic nitrogen right out of the air and convert it into a usable form in the soil. Without this massive, invisible biological labor force, ecosystems worldwide would just instantly collapse. No joke.
So who are these heroes?
They are highly specialized, incredibly diverse bacteria. Some, like Bacillus, Klebsiella, and Clostridium, just roam completely free living in the soil. Others form tight, super intimate partnerships with plants. You've got rhizobium bacteria, which live securely inside the root nodules of legumes, while Frankiobacteria partner up with non-legumes like alder trees. And we absolutely cannot forget cyanobacteria, which are remarkably adaptable. They can live freely or forge symbiotic relationships, just like they do in lichens.
But, this relationship isn't charity. It is a strict economic transaction. We call it the microbe economy, and it's heavily tied to the flow of carbon currency. To get just 20 milligrams of usable nitrogen, a plant has to pay the bacteria 1 whole gram of carbon energy. That is a steep, expensive price tag. In fact, if the soil already has enough available nitrogen, the plant simply won't pay it. It flat out refuses to spend its hard-earned carbon to host these microbes if it doesn't absolutely have to.
All right, Section 4, Chemical Transformation in Soil. Because once the nitrogen is finally secured in the dirt, the intricate chemical machinery down there is really just getting started.
We need to talk about nitrification. This is the biological process where specialized soil bacteria oxidize ammonium into hydroxylamine, then into nitrite, and finally into nitrate. Basically, think of the soil as a giant kitchen where raw nitrogen is slowly, deliberately cooked into the primary food source that plants can easily drink right up.
Let's walk through this step-by-step chemical cascade. First up, bacteria called Nitrosomonas grab ammonium and oxygen, creating hydroxylane and then nitrite. But here's the thing, nitrite is actually toxic. So a second group of bacteria, Nitrobacter, immediately steps in to convert that nitrite straight into nitrate. This elegant two-step microbial relay race is happening constantly, 24/7 in healthy soil.
Now, here's a crucial point. What the plant actually eats changes the soil's chemistry. If a plant takes up nitrate, which carries a negative charge, it has to maintain its electrical balance by pushing a negative charge, like bicarbonate, back out into the soil. That actually increases the soil pH, making it more alkaline. But if it takes up positively charged ammonium, it pushes out a positive hydrogen ion, which decreases the soil pH and makes it more acidic. This is absolutely vital knowledge for farmers who are trying to balance the acidity of their land through targeted fertilizer use. It's all connected.
And that leads us to our final part, Section 5, Losses and Natural Balance. Because in nature, what goes into the soil must eventually find its way back out to maintain the grand cycle.
This natural escape route is called denitrification. In environments lacking oxygen, like really waterlogged soils, bacteria are forced to use nitrate instead of oxygen just to breathe. As they strip the oxygen molecules away, the nitrogen changes forms. It goes from nitrate to nitrite to nitric oxide, then nitrous oxide, and finally, right back into the nitrogen gas that floats straight up into the atmosphere. Full circle.
But biology isn't the only way nitrogen makes its escape. There is a surprising real-world inefficiency known as ammonia volatilization. When we apply animal waste or urea fertilizers to soil, a massive chemical reaction kicks off with the water. Up to 50% of that carefully applied nitrogen simply evaporates directly into the air as ammonia gas before the plants can even touch it. Literally half the nutrients, just vanishing into thin air. Crazy, right? So we've seen how meticulously microbes, plants, and soil chemistry negotiate this incredible cycle, trading carbon for nitrogen, balancing acidity, and naturally recycling gases back up to the sky. But it leaves us with a pretty vital question to think about. If nature balances its nitrogen economy so carefully, counting every single milligram against carbon, what happens to our local ecosystems, our waterways, and our atmosphere when human fertilizers suddenly overload this delicate microbial market? Thank you so much for joining me for this explainer. I'll see you next time.